Hi everyone, welcome back to chemistry. So in the last video, we talked about the combined gas law at the very end of the video. And that one's really cool because it compares pressure, temperature, and volume from, an initial sample versus a final sample of gas. But today, I want to talk about the ideal gas law, which is a gas law that relates all of these different properties of a gas, even more so than the combined gas law, under any condition, rather than when you have kind of like a change in conditions. So there's not going to be some kind of initial pressure versus a final pressure or something like that. It's just looking at all of these different properties of a gas at once. So the ideal gas law is PV equals nRT. So let's break this down just a little bit. So P here stands for pressure, the pressure that your gas is at. V stands for volume. N, lowercase n, stands for moles, the number of moles of your gas that you have. R, I want to talk about in just a second, and T stands for the temperature of your gas, again, in Kelvin. Okay, got to convert to Kelvin, just like any of the other gas laws. And then R is this special value called the ideal gas law constant. And it's this constant that relates all of the values of pressure, volume, amount, and temperature of a gas sample, or sometimes I just refer to it as the gas constant. So the value of R depends on which units are used to express the other quantities. So for instance, when we're plugging in our R into our equation up above, right? In order to get a bunch of these units to cancel out and to solve for whichever unknown you're looking for in the given problem, you have to be, using the same units. So if you'll notice that these units on each of these R values, these gas constant values, they're the same except for the pressure units. And that's to allow us to use different units of pressure in our ideal gas law, either ATMs or millimeters of mercury. It is typically more common, especially for my class, to use this R value. So when you're working out problems on an exam, that's the one that I'll probably put on the exam and ask you questions using. But the other one exists as well. But usually for these gas constants, these will be given to you on an exam. You don't need to memorize them. And the way it works is you just plug this value in for R in your ideal gas law, okay? And you can solve for your unknown and make sure you get to cancel out some of those units. So let's practice this a little bit. So this is an ideal gas law problem. So we're going to need our PV equals nRT, our ideal gas law. And this is actually my favorite gas law. I forgot to mention that above. I actually also have a way of memorizing it. It's PVNRT. Sometimes you'll hear people say that, PVNRT, PV equals nRT. And it's a really useful equation because it's the only one of our equations that takes into account the number of moles. Okay, so the amount of our gas in our sample. So let's try this out. So it says, what is the temperature of a 0.52 mole sample of a gas with a pressure of 1.2 atmospheres and a volume of 10.7 liters? Okay, so let's break this down a little bit and make sure that we have all of these parts of this equation. So let's do our color coding. So it looks like I have a pressure in 1.2 ATMs. So we've got a pressure. We've also got a volume, 10.7 liters, so we'll highlight that as well. We've got our volume. We've got our number of moles, and this is new to us now, so let's do green. Our moles can go in for N, right? We said that lowercase n stands for the number of moles of gas you have. We have our R, right? That's our gas constant, so we always have that one available to us. So let me just, I'll write that over here. Our R equals, now let's see which R we want to use. Looks like we've got our pressure in units of ATMs. So we're going to use the gas constant that has atmospheres in it, and that's going to be 0.0821 liters times atmospheres over moles times kelvins. And I know those units look really crazy, but we'll talk about them. All right, and then temperature is the thing that we're solving for, right? It says, what is the temperature? So we're solving for that one. That's our goal. So let me put a question mark there because that's what we're looking for. All right, so let's copy this down here, our PV equals nRT, our ideal gas law. And I want to go ahead and solve for temperature and then plug in all my values. So in order to get, these are all being multiplied together, right? So in order to get that temperature alone, we got to divide by N and R on both sides. It's going to allow us to cancel those out. And then I'm left with T equals PV, pressure times volume, over moles times our gas constant. All right, so T equals, our pressure is 1.2 ATMs. Our volume is 10.7 liters. Our number of moles is 0.52 moles. And our gas constant is 0.0821 liters times ATMs over moles times kelvins. Okay, so let's take a look at those units here, and let me zoom out just a bit. We can cancel out a lot of these units, so let me show you how that works. So over here, I've got atmospheres in the numerator and atmospheres in the numerator of the denominator. So what ends up happening is we can cancel those out. So let's cancel out those atmospheres. All right, we can also cancel out our liters because of the same idea. We've got liters in the numerator here and liters in the denominator over here. So let's get rid of that one. Moles also cancel out. We've got them in the numerator here and the denominator of our fraction over here. So we can cancel those out as well. And we're left with units of Kelvin. And now it looks really funky, but let's take a look at this. So let's get some number out of this. Oops. And then I'll show you how those units work out, because right now it looks like they're in the denominator of the denominator. So that's kind of strange. So T equals 300. All right, and then let's think about these units. So let me zoom in a little bit over here. That's a little too far. So anytime you've got a fraction, really what you can do is you can separate that fraction into two things. So we have 300 here is technically in our numerator, right? 300 divided by 1 is the number that we have over here. And then we can say that we're multiplying that by 1 over Kelvin. Okay, so now I want to convince you that this is the same thing as this. Okay, and why is that? Now we gotta get a little mathy here. So notice that we've got 1 over Kelvin. Well, another way that we could express that is 1 times K over 1. Well, what's 1 times K over 1? Oh, that's just K, right? All right, so if you don't believe me after all those steps, or if that confused you more, you can just take my word for it, right? That after you cancel out all of these units that I've canceled out in blue, you're going to end up with units of Kelvin. And that's great because we wanted to end up with units of temperature, right? And temperature, when we report temperature using these gas laws, that's going to be in kelvins. All right, let's try this one more time. So it says, what is the pressure of a 0.32 mole sample of gas in a 6.2 liter container with a temperature of 25 degrees Celsius? Now, my other tip is anytime you see moles in one of these problems where you're kind of trying to use gas laws, you're not going to be told right away in this problem, right, that you have to use the ideal gas law. That's your job to figure that out by labeling all of the different parts of that you're given in the equation. But my biggest hint is that anytime you see moles, you know you're going to have to use PV equals nRT. You know you're going to have to use your ideal gas law because your ideal gas law is the only one that has moles in it, right? Is the only one that has the lowercase n. Okay, so that's kind of the nice thing about the ideal gas law is you know kind of immediately whether you need to use it or not, based on if you see moles in your problem. Okay, so we've got moles. What else do we have? It looks like we've also got a 6.2 liters is a volume, right? Liters is a unit of volume, so that's going to be our volume. And then it says we have a temperature of 25 degrees Celsius. Uh-oh, we got to convert that though, right? So let's actually convert first. So 25 degrees Celsius. We said that for Kelvin, we have to add 273. So that's going to be 25 plus 273, which is 298 Kelvin. So let me go ahead and highlight that. That's our temperature. And then our pressure is the thing that we're solving for. So that's what we don't know. And then what about R? Yeah, R we know, right? R we are always given, whether probably on the first page of your equation sheet in your exam, or somewhere else on your homework or something like that. But the one that we're going to use today is 0.0821 liters times atmospheres over moles times kelvins. And the reason that I chose to use that gas constant instead of the other one that has millimeters mercury is just because this question didn't specify what units of pressure it wanted at the end of the problem. So I just picked the one I'm most familiar with, which is the one I've written up there. All right, so let's see. So we got to start. We got PV equals nRT, and we want to know, we want to solve for our pressure. So let's divide both sides by volume, and that allows us to cancel out those volumes, and we're left with nRT over V. So let's plug this in. So we got N is our number of moles, which is 0.32 moles. R is our gas constant, 0.0821 liters times atmospheres over moles times Kelvin, crazy units. Temperature we just solved for is 298 Kelvin, right? We had to convert to Kelvin first. And then our volume is 6.2 liters. Now, I do want to say sometimes in some problems, especially in your textbook too, you'll see sometimes they'll give you that volume in milliliters. So you do need to convert to liters first. Why? Well, your gas law or your gas constant is given to you in liters times atmospheres over moles times Kelvin. So in order to cancel out those liters and compare apples to apples, you got to have them in the right units. So you got to have them in liters. So, but that's okay. You know how to convert from milliliters to liters, right? All right. So let's figure this out so we can cancel out lots of these units here. Well, I know I have moles in the numerator and moles in the denominator here, so we can cancel those out. We've also got Kelvin over here and Kelvin over here, which cancels out. We've got liters in the numerator and liters in the denominator. So that cancels out. And then we're left with ATMs, which is great because we are looking for units of pressure, right? Okay, so let's get a number out of this. And that gave me 1.3 ATMs. My calculator spit out 1.26, so I'm going to round that to 1.3 so that we've got just 2 sig figs, and that is my final answer. So the pressure of this sample of gas is 1.3 atmospheres. All right, so scientists said, we came together and we said, look, for convenience, it would be nice if we could have this thing called standard temperature and pressure, where when we're talking about a gas, we can say, hey, I'm looking at a gas sample that's at standard temperature and pressure, and this is what I'm noticing about that gas. So we've defined a standard temperature and pressure, or sometimes called STP, as 273 Kelvin or 0 degrees Celsius for our temperature, and 1 ATM of pressure, 1 atmosphere of pressure. And those two are standard temperature and pressure. So anytime I say, hey, I have a gas at STP, you know both the temperature and the pressure. And then you can also use the ideal gas law to determine the volume of 1 mole of gas at STP. And when you plug in all of those numbers, right, assuming you've got 1 mole of gas, your standard temperature and pressure is 1 atm and 298 Kelvin, and then we've got our gas constant, our R value there. When we plug in all those values, what we find is that the volume we get for our gas, right, we're solving for volume, is 22.4 liters. And this is true for any gas at standard temperature and pressure. We find that based on the ideal gas law, regardless of what gas we have, if we have 1 mole of a gas, any gas, that's going to equal 22.4 liters of that gas at standard temperature and pressure. All right, so let's try this out. So this says a sample of gas at STP. So I'm going to underline that. So we know some stuff already. We know our temperature and we know our pressure, okay, just right off the bat. Has a volume of 40.5 liters, so we know a volume as well. And then it wants to know how many moles of the gas are present in the sample. Okay, so we have a temperature, 298 Kelvin. We have a pressure, 1.00 atm, right? All of that just from seeing this at STP. We got both of those numbers. And then we have a volume, 40.5 liters. And then we want to know how many moles of gas are present. Okay, well, remember I said anytime you're looking for the number of moles of your gas, we're going to need our ideal gas law. So we're going to need PV equals nRT. And now it looks like we know all of the parts of this equation, right? Our R value we've always got, right? That's looks like we've got ATMs here, so we're going to use our 0.0821 liters times atmospheres over moles times kelvins. And we can plug in all of those values and solve for our unknown, which is N in this case. So again, I'm going to divide both sides by R and T to get N alone. And that's going to give me N equals PV over RT. And now let's solve for N. So we've got our pressure, which is 1.0 atm, or 1.00 atm. We've got our volume, which is 40.5 liters. And then we can divide by our R value, our gas constant. And our temperature, which is 298 Kelvin. And we can get out a number from that, which I got let's do 1 point, looks like 66, because we want 3 sig figs all around, looks like. And that is moles. So at standard temperature and pressure, this sample of gas, there are 1.66 moles of our gas present. All right, the final kind of gas law that I want to talk about is called Dalton's law. Dalton's law of partial pressures, named after John Dalton, who we talked about when we talked about atomic theory. So sometimes you'll see this as Dalton's law of partial pressures or just partial pressures. But what John Dalton reasoned was that gases usually consist of mostly empty space, right? Anytime you're looking at these gas samples, they're so far apart from each other, like we talked about in a previous video, that those gas particles are mostly kind of roaming around in empty space. So he said that these gases, even if there's a mixture of gases in a container, they're mostly going to behave independently because they're just coming in contact so infrequently with each other. They're mostly surrounded by empty space. So he found out that each component in a mixture of gases contributes to the total pressure in that mixture of gases. And this is called Dalton's law of partial pressures. So for me, I always think this is a little bit easier to understand actually with this mathematical equation, which says that the total pressure in any given gas mixture sample is equal to the sum of the partial pressures of the different types of gases in that sample. And this sounds really complicated, but once we work out the problem, I think you'll find that you actually like this law a lot. So let's try this out. It says that the total pressure of a mixture of O2, oxygen, and N2, nitrogen, gases is 1.3 atms. That's the total pressure, okay? So we would write that as P total. If the partial pressure of oxygen is 0.54 atms, what's the partial pressure of nitrogen? All right, so in other words, we've got this mixture of gases, oxygen and nitrogen gases, in a container. And we know that the total pressure of that mixture is 1.3 atms. That's our P total. So what Dalton's law of partial pressure says is that the total pressure exerted in that container by those gases is equal to the sum of the partial pressures of each of those gases. So if oxygen is exerting a partial pressure of 0.54 atms, we can call that P1, or just sometimes you'll see, PO2, and that's just to say the pressure due to oxygen, okay, plus the pressure due to nitrogen. And we could call that PN2, right? The pressure of nitrogen. N2 over here and O2 over there. That's where I'm getting those subscripts from. All right, so let's rewrite this equation a little bit. So we've got our P total equals the pressure due to oxygen, the partial pressure of oxygen, plus the partial pressure of nitrogen. Now, if our P total is 1.3 atmospheres, and we were given our partial pressure due to oxygen, which is 0.54 atmospheres, then we can solve for the partial pressure due to nitrogen, right? Let me finish this color coding here. Okay, and that just becomes a simple algebraic equation, right? So we can subtract 0.54 atmospheres from both sides because we're adding it on the right. So we got to do the opposite, subtract. Okay, and then we can get that the partial pressure due to nitrogen gas is 1.3 minus 0.54, which is going to be 0.76 atmospheres. You could have also been given, right, your partial pressures of your different gases in your mixture and been asked to figure out the total pressure. And in that case, you just need to add up all of those partial pressures. Okay, so I hope I convinced you that it's not too bad, this Dalton's law of partial pressures, even though sometimes it can look a little scary, along with the ideal gas law. And if you have any questions, as always, let me know, and I'll see you next week for Chapter 9.